Hey there team, Chemistry Coach coming at you with a new video, but sort of like a part 2 video from standard enthalpies of formation, because now that we know what standard enthalpies of formation are, what standard states are, what reference forms are, all this fun stuff, we can use them to calculate what we're really after. This whole chapter is about how do we get the heat of reaction. Again, we could say standard enthalpy of reaction or standard heat of reaction, but if we're at constant pressure, again, we can use those interchangeably, right? Heat and enthalpy. So this is the new one for us. All of the heats of reaction we've done before have not been at standard state. So we got that little degree or not symbol there. Yay! So this is one of the ways we can theoretically do it, right? So we looked at coffee cup calorimeters. We looked at bomb calorimeters. We looked at using bond energies. And now we're doing standard enthalpies of formation. All right. I'm going to skip the derivation of this. You can read it in the textbook if you want to. But in general, if you want to determine a standard enthalpy or heat of reaction, right? So we got a balanced chemical equation for some reaction that's occurring, doesn't matter what it is. And we want to use standard enthalpies of formation values from your appendix or some table. Usually, I mean, I've only seen the tables personally at 25 degrees Celsius or 298.15 Kelvin. We can use this equation, which should look pretty similar, right? So the standard enthalpy of a reaction is equal to the sum of the stoichiometric coefficient of the products, right? So these little terms, these little new symbols here are the stoichiometric coefficients from the balanced chemical reaction. So if your reaction is not balanced right, your thermodynamics are toast. So we take the stoichiometric coefficient, which we treat as an exact number, for the products, look on the right-hand side of the arrow, times their standard enthalpy of formation values, which are tabulated in the back of your book or on tables that are provided. So we don't need, from the last video, we don't need the equation showing the formation of that particular substance from its elements in their standard states and reference states. We don't need that anymore because we have the value. I just wanted to find what that meant. What those values in the back of the book, what are those? But if we take all the products and take the tabulated value for the standard enthalpy of formation in kilojoules per mole, times it by the stoichiometric coefficient in moles, and then subtract from that the exact same thing for the reactants, the sum of all the standard enthalpies of formation. I have trouble connecting my triangles for some reason. It's bothered me. Sloppy. I take all the standard enthalpies of formation times the stoichiometric coefficient from the balanced chemical equation, and that result will be the overall for the equation. Hey, pretty cool. That should look familiar when we did a similar thing with bond energies. Right? When we estimated heats of reaction using bond energies, it had those summation terms, right? So we took the energy it took to break all the bonds of the reactants and subtracted the energy to form all the bonds of the product. So it's a little bit different. It's flipped that way, the way the tables are. And we're going to see this again in next semester. We're going to see this again when we look at entropies. Right, we'll be able to calculate the entropies of reaction under standard conditions and the Gibbs energy, and the equations look almost identical. So picture this one in your brain. Pretty straightforward. It takes a while. So these are tedious calculations. They take a bit because you got to look up the values in tables and do all the mathematics and all the steps, but they're very easy to do. Right, just multiplying some numbers here and here, summing them, take this value minus that. So get this total value first. Get that total value second, and then just subtract them, right? And since these are exact, right, we're going to be limited. It's going to be pretty much just addition. It's an addition type problem, so we're going to be limited by decimal places or limited by the largest absolute uncertainty from the values in the tables, right? So you just look up the, what are the absolute uncertainties here, and that's what's going to limit you throughout your calculations. And if it's an element, right, it's going to be 0 most likely if it's its most stable form. So let's do a couple examples. And I think we're pretty good. These are straightforward calculations. Be right back with an example. Yay! These types of problems are all exactly the same. It's just different species, different states, different numbers, but the approach is exactly the same. And on my exams, I give you the equation, right? You don't have to memorize it, but you will. When you use it or not, you memorize things. So here's a typical problem you might see on an exam or quiz, right? So let's calculate the standard enthalpy or heat of reaction for the following reaction. Boop! Provided they are for your viewing pleasure, at 25 degrees Celsius. Now, at this level, if the temperature is not stated, we're going to have to assume 25 degrees Celsius or 298.15 Kelvin, i.e. roughly, that's pretty nice toasty Southern California room temperature, right? In the lab, I'm sweating at what is 25 degrees Celsius. Get that sweat in the goggles. You need those little windshield wipers. So I will try, if I forget to state the temperature on an exam, it would be best to raise your hand or something like that and say, well, what temperature is this at? Because remember, these are technically temperature dependent. And I'll be like, shoot, I forgot to mention, it's at 25 degrees Celsius. Because if it's not that, we can't really use that table, right? Oh, no. Unless we make the assumption it's temperature dependent, which is not. And we're at standard conditions, which I don't really have to state because, right, that's a little redundant, right? I put that little not symbol there, so it's at standard temperature conditions, so technically didn't have to write that one. Using standard enthalpies of formation values. All right, so we got 2 moles of ammonia gas. The state's critical, right? Plus 2 moles of oxygen gas, giving us dinitrogen monoxide gas, 1 mole of that, and 3 moles of liquid water, right? Pretty straightforward. I mean, see if you can approach this on your own, right? So let's write the equation down, and we're going to take the products minus the reactants, right? So let's write that equation down. We're going to take the 1 mole of the dinitrogen monoxide gas. So look it up on the table, right? Look under nitrogen or oxygen, probably under nitrogen. See if you can find the value there. You're going to take 1 times that, and then 3 times the water. So find the water on here and multiply that by 3 and add those together. That'll be your first term. And then we take the reactants and we take 2 moles times the ammonia gas value you can find in the table, probably under nitrogen there. It might be under hydrogen, but it's one of the two. And then 2 times oxygen gas, but that's an element, right? That's its reference state, most stable form. So that's going to be 0. So we don't have to look that up. If you know that, it saves you a little time on an exam. You're like, oh, where's the oxygen? Right. And you waste 15 seconds to look for it. You go, oh, it's 0. Oh, darn. Right? Flat forehead syndrome. I knew that. And add those terms together and then take that term minus that term and you get your overall value. And look at each of the standard enthalpies of formation and just look at the absolute uncertainty of each one. The one with the fewest number of decimal places per se is what your answer will be. So it's fairly easy to track uncertainty on these. Kind of like when you're calculating molar masses of compounds. You look at all the elements on the periodic table, and it's technically one gigantic addition problem. You're just limited by the fewest decimal places, whichever element has the fewest decimal places. Same idea here. Give it a shot. I will write the equation up here real quick for you, and then I will not have room. I'll have to do it on another board. So let me pause this, write the equation up, and let's see what you get. All right, just to reiterate, there's our equation. I personally will give you that on a test. Not every instructor is going to give you the equation. Some might make you memorize it. Hey, whoever your coach is at the time, go with their rules, right? So we're going to take the products. So we'll take the 1 times that value plus 3 times that value and add them together, right? And then over here, we'll take 2 times that value plus 2 times that value, which is 0. Add them together and then subtract those 2 terms. I like to keep those in brackets. Give it a shot. See if you match what I get. I'll write it up on the next board. Like I said, these are not difficult, but they're tedious because you're looking up values on tables, or if you're on your homework, flipping through your big, gigantic textbook or something. All right, so I rewrote the equation, and I had the balanced equation there, and then we had the delta H definition on the last board. So we're going to take the sum of the products minus the sum of the reactants. So let's take our 1 mole of dinitrogen monoxide gas. Let's look it up on our table. So probably under nitrogen. All right, so here's nitrogen. And I don't have my glasses on, but that looks like dinitrogen monoxide to me. All right, so you see the 82.05 kilojoules per mole. Right? So usually it'll state on the table, right? It's kilojoules per mole. And again, this is at, I didn't put on there 25 degrees Celsius. I'm going to have to add that to mine. So I'm going to take 1 times that value. And then I'm going to take 3 moles of liquid water. And that was not oxygen. So it looks like that's under hydrogen. So let's look under hydrogen here and go to, that's hydrogen peroxide. And that's gas phase water. So we want liquid water right there, which is negative 285.8 kilojoules per mole. And we do that by 3. And then we're going to subtract from that the sum of the reactants. So we're going to take 2 moles of ammonia gas. Let's look up that value. That was under nitrogen, right? Oh, that's aqueous. So here's nitrogen, and we want NH3 gas, not aqueous gas, which is the negative 46.11 kilojoules per mole. Boop! Right? The hardest part for me is finding the damn things. I don't have my glasses on. I'm like, I can't read. And then 2 moles of oxygen gas, understanding that should be 0, right? That's the reference state of oxygen. But if you panic on a test, you'll be like, oh, that's right. Oh, I knew that. Right? Monatomic oxygen and triatomic ozone are not. So let's take 1 times 82.05 plus 3 times negative 285.8, right? That's good to 2 decimals, good to 1 decimal, so we're limited to 1 decimal place. That gives us negative 775.35 kilojoules, good to the 10th place, right? And that's everything for all the products. And let's do it for the reactants. 2 times negative 46.11 plus 2 times 0, right? So we're just limited to 2 decimals, so that times 2 would be negative 92.22 kilojoules. And then we're taking the products minus the reactants. Of course, here we're subtracting a negative, right? So it's going to be a little less negative than that. So negative 775.35 kilojoules minus negative 92.22 kilojoules. That's good to 2 decimal places, or the 100th place. That's good to 1 decimal place, the 10th place. So we're good to the 10th place. I get negative 683.130 kilojoules. Good to the 10th place. That's not going to round up, so it stays as negative 683.1 kilojoules. Now, we'll find in some scenarios we can leave that in kilojoules, but sometimes we need that as kilojoules per mole of reaction. If we take that value and do some other stuff, which we will do a lot in second semester general chemistry. So when we're doing Gibbs energy and a whole bunch of stuff like that, we may need to use the kilojoules per mole. It's situationally dependent. So I'm okay with either unit based on what you're calculating out. And that's the same for everything. Let's do one more with ions, right? Talk about ions in solution a little bit, and we're done. Because what's the point? It's the same thing over and over and over. You got better things to do with your life. All right, example number 2. This will be our last one. So again, think of this video and the prior video on standard enthalpies of formation as just 2 sides of the same coin. You need them both together. So let's calculate the standard enthalpy or heat of reaction for the precipitation of calcium phosphate at 298.15 Kelvin, which would be 25.0 degrees Celsius or 25 degrees Celsius if you define that temperature exactly. So first, I didn't give you the equation on this one. Oh, you're so mean, teacher. So we're forming some calcium phosphate. So we need some calcium ion, right? So calcium's a plus 2. And phosphate, I may need to move that arrow over. Phosphate's a minus 3. Should be pretty easy for you. Remember the beginning of the semester, this is probably hard for you. These were actually questions on exams. Those are not equal and opposite, so they don't go into 1-to-1 ratio. So we need the lowest common multiple of 6. So we're going to need 2 phosphates and 3 calcium, right? So let's take calcium phosphate. There's the precipitant. Now that's not balanced, is it? So we need 3 of these. And 2 of those, my friends. So let's calculate the standard heat of standard enthalpy of a reaction for that. Because that's not the elements in their standard states, right? These are the ions. So this is not a standard enthalpy of formation reaction. This is a precipitation reaction. So do the same thing. Get your equation. So we know delta H. And by definition, I didn't have to state I did on the last problem. I stated standard conditions, but it's defined as standard conditions. And we're probably going to be obviously using standard enthalpies of formation. I gave you the proper temperature so we can use the appendix or tables that are provided. So let's take the sum of the stoichiometric coefficient of the product, which is a 1, yay, times delta H naught formation, and subtract the stoichiometric coefficient of the reactants, the 3 and the 2, times their standard enthalpies of formation. So we look up the calcium ion and the phosphate ion. And again, for solutions, we need a defined 0 state. So I'm just going to make a statement here. So it uses H plus aqueous in solution as a 0 reference. Right. Now, for my class, we use the hydronium ion an awful lot, but unfortunately, most tables and most textbooks, especially when we get to electrochemistry next semester, we can't get away from the H pluses in a lot of scenarios. So anyway, that is defined as 0, and every other ion is referenced to that, just like the carbon-12 isotope is defined as 12 AMU, and every other atomic mass is relative to that. So that's our reference. So let's take, even though we don't have it in here, it's not important, but you'll see on the table, if you find H plus, that has a value of 0 right on. So H plus aqueous is the 0 state in solution. So just look up calcium phosphate and calcium phosphate on the tables, right? Look in your appendix. So you can look on my table if you have it. If it's not there, remember, it's not a complete table. You can find it in the back of your book for my class. I think that's Appendix D. So calculate it and see what you get, gang. I need another board, obviously. All right, did you get what I got? Well, let's take a look. So we need to look up in your tables for these particular values. So we're going to get 1 mole of calcium phosphate. Now, on my tiny little thing, I don't have calcium on here. So if you look in your appendix, you'll find calcium phosphate is negative 4,121 kilojoules per mole, referenced to H plus aqueous as 0, right? And that's it. We only have that one product. Yay, isn't that nice? And then we're going to take 3 times our calcium plus 2 times our phosphate. So let's take 3 moles of the calcium ions. And calcium I don't have on my little thing. So if you look in your appendix, calcium is negative 542.8 kilojoules per mole. Times that by 3. And then we're going to add, because of the summation, 2 moles of the phosphate ion. And I think I have phosphate on here. Yeah, I've got phosphate on here. So phosphates right there, phosphate ion. Right, relative to H plus ion is the negative 1277. Boom. So limited to the ones place there, tens place, ones place, so limited to the ones place there. So when you do the 3 times negative 542.8 plus 2 times negative 1277, you get negative 4182.4 kilojoules, good to the ones place. And then we take the total amount from the products, negative 4121 kilojoules, minus the total amount from the reactants, negative 4182.4 kilojoules, limited to the ones place, I get 61.4 kilojoules. That does not round up, so it stays at 61 kilojoules, or you could say kilojoules per molar reaction in that scenario. Yay! The ramifications of that we'll talk about a lot more in second semester of general chemistry. So you can now calculate fairly decent heats of reaction values, in this case, standard conditions, using standard enthalpies of formation. You can also estimate values using bond energies, like we did in the last chapter, and you can experimentally determine them using bond calorimeters, mostly for heats of combustion, and using coffee cup calorimeters for like neutralization reactions, even though we tend to use coffee cup calorimeters a lot in lab to determine specific heat values of metals. We've got one more left. That's it for this particular chapter that I'm going to be covering. We can calculate heats of reaction using Hess's law. Ooh.